Now we'll see the equation for continuity of current or continuity equation for current. Here we understand how the current flows or the flow of charges is continuous with respect to time t. We are going to see that there will be a continuous current with respect to time t. To see that, let us consider a volume, a cuboid of volume V consisting of finite amount of charges. Here I have just represented one of the charges as Q, but it consists of finite number of charges inside, and let rho be the volume charge density. Let rho be the volume charge density. In this volume, as this volume is getting expanded, there is a flow of charges. As this volume getting expanded, there is a flow of charges. That is, the rate of flow of charges with respect to time t takes place as the volume is getting expanded, and that is nothing but current. That is nothing but current. So, current in an enclosed surface, this current in an enclosed surface area of surface S is always given by I is equal to minus dq by dt, the rate of change flow of charges. Dq by dt is nothing but rate of flow of charges with respect to time t. That I have taken as equation 1. Now, the same current can be expressed in terms of current density. Before that, the negative sign of the equation 1 indicates that whenever there is an expansion, the volume charge density decreases. Means whenever there is an expansion or the flow of charges, the charge density inside the volume decreases. That's what the negative sign indicates. The amount of charges inside the volume decreases as they flow out of the volume or as the volume expands. So in the enclosed surface of volume V, there are 6 faces. In this enclosed surface of volume V, there are 6 faces of each of surface area S. 6 faces each of surface area S. So, the total current will be surface integral of the current density. The total current will be surface integral of the current density. So, I have written current I is equal to surface integral of the current density J in an elementary surface ds. That is taken as equation 2. From equation 1 and 2, I have substituted in the place of I, that is surface integral of J into ds is equal to minus dq by dt, taken as equation 3. Now, applying the Gauss divergence theorem, which states that surface integral of a vector is always equal to volume integral of divergence of that vector. So, this I wanted to convert it in terms of volume integral. So, only we have considered Gauss divergence theorem, and according to that I can write it as surface integral of a current density vector J is equal to volume integral of divergence of that vector J in an elementary volume V. So, as per the volume charge density, we can write Q is equal to volume integral of the charge density dV. Volume integral of charge density dV, which is taken as equation 5. So, from 4 and 5 in equation 3, substituting in the equation 3, we get volume integral of divergence of vector J is equal to minus d by dt of, in the place of Q, I have taken volume integral of the charge density rho. So, rewriting the above equation, we get volume integral of divergence of the vector J in an elementary volume V is equal to minus volume integral of d rho by dt in the elementary volume V. So, we got left hand side in terms of volume integral, right hand side also in terms of volume integral. Have taken both the terms, one side left hand side and equated right hand side to 0. And since both are volume integral, I have taken that common outside and equating that to 0. Here only possibility is divergence of J plus d rho by dt is equal to 0, as the volume integral of dV cannot be 0. So, divergence of J is equal to minus d rho by dt. This is the equation for continuity of current. It shows that current flows continuously, or the charges flow continuously as and when there is an expansion of the volume. And for steady state, means if there is no flow of charges, for steady state, this change in charge density will be 0. That is, d rho by dt will be 0. When d rho by dt is 0, current density, the flux or the divergence of current density J is equal to 0. So, this is what the equation for continuity of current.